In this video, we're going to look at solving radical equations, or equations containing radicals. For example, something like the square root of x equals to 5. Now, the strategy on this is going to follow the same strategy we have been using. We want to undo what is happening to the x. So here, the x is being square rooted. The way you undo a square root is you square it. So we need to square both sides. We square the left in order to undo the square root. We square the right because whatever we do to one side of the equation, we have to do to the other. Then the result is x equal to 25. So that's the general idea. We want to undo the square root, so we square it. If we happen to have a cube root, we would undo that by cubing it. Now there are a few curveballs that we need to talk about with this. They're not too bad, but the first one is that we can't always trust the solving steps of this process. I'm going to give, for example, I'm going to build an example that explains the issue well. So let's say we're asked to solve the square root of x equal to -3. Now before we launch into this thinking of, okay, I need to undo the square root, so I'll square both sides, let's think about this. This is saying what number, in terms of the x, when we square root it, do we get a 3? Do we get a -3? Well, the number that would need to be square rooted there, let's just go ahead and go into our undoing process. So I'll square the square root, I'll square the -3, square both sides of the equation. On the left I get an x, and on the right I get a 9. So this is saying that the square root of x squared equal to -3, that the solution is a 9, which means if I plug 9 in for x in the original equation, I'll get a true statement. In other words, this is saying that the square root of 9 equals -3. And that's not true. Now, we didn't do anything wrong. We squared correctly, but we got that the square root of 9 equals a -3. That's not a true statement. What that means is that this equation has no solution. Basically, because of the weird way that radicals and squaring work, square rooting and squaring work, and how they deal with negatives, it creates this issue where we can sometimes get solutions to our equation that weren't solutions to the original equation. These are called extraneous solutions, and what it means is we're going to have to check our answer every single time. Every time we come down and we get a value for x, we're going to have to go back and plug it into the original equation to check to see if it actually works. The reason for that is the properties of equality are a little different when we square both sides of an equation. Usually the rule is we can do whatever we want to one side as long as we do it to the other. And the idea of that is we're keeping the same solution set as we work through the problem. With radical equations, with square root equations, it's more like we're not losing any solutions, but we may gain some solutions along the way. Let's look at another example. Alright, let's say we have the square root of x plus 2 and then plus a 3 equal to 7. So when we have multiple things happening on one side of the equation, we want to follow the same strategy we did when we were using the square root property on quadratics. In other words, I do not want to start out by just squaring this side and then squaring the 7. Now ultimately I do want to square root this square root, but when I square a side of the equation, I have to square the entire side of the equation, and we cannot just apply this square to the individual terms. We would have to distribute all those terms out. We can't just distribute the square. So what I want to do in situations like this is the same I did when I was working with x squareds, is I want to isolate the square root first, get it by itself on one side of the equation, and then start my undoing process. I want to isolate the monster, and then I want to eliminate the monster. So I want to start by getting the square root piece by itself on one side of the equation by subtracting 3 from both sides. That's going to give me the square root of x plus 2 equal to 4. And then I want to go ahead and square both sides. When I do that on the left, the square root and the square will cancel each other out. That gives me x plus 2. On the right, I'll get a 16. Now in this case, I'm not done solving for x, but all I need to do to finish it off is to get x by itself by subtracting 2 from both sides. That's going to give me x equal to a 14. But no matter what, we're not done yet. We have to take whatever solution we come up with and we have to check it back into the original equation. I like to say with radical equations, we're not finding the solution so much as candidates for solutionhood. And then we have to go back and check if they actually qualify. So we have to check, and we're not saying these are equal. In this case, we're actually checking to see if they're equal. I help keep my brain in check on that by putting a little question mark above the equal sign. So square root of 14 plus 2, that's the square root of 16, which is 4, plus 3. And we're asking, does that equal 7? I think it does. So we can say, hey, 7 equals 7, yay. And then we can decide that 14 actually is a solution to the original equation. So that's the general idea with solving these guys. Whatever your radical piece is, you're going to get it by itself on one side of the equation, and then you'll square both sides of the equation. If it's a cube root, you'll cube both sides of the equation. If it's a fourth root, you'll raise both sides to the fourth power, and then simplify whatever needs to continue to happen after that. But then remember, you always have to check your final solution candidate in the original problem to see if it actually works. Go ahead and give some of those a try and see how it works out for you.